All right, good morning, everyone here on the campus and those following the live stream. Welcome to Saturday Morning Physics on this unusually warm November day. I'm Professor Christine Adella from the Physics Department, one of the organizers of Saturday Morning Physics, along with our team, Professor Tim Chupp, Monica Wood, and the Demo Lab staff, and Carol Raybuck. Before moving on to our program, I want to remind you that Saturday Morning Physics is made possible by you, by your many generous contributions as Saturday Morning Physics fans, and by the energy and presence that you bring here along with your questions. For more about supporting Saturday Morning Physics, go to saturdaymorningphysics.org. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Pulikeshi Dayalu Astrophysics Fund. Before moving on, I want to note that today's event will conclude with the traditional Saturday Morning Physics Q&A at the end. For those joining online, please send your questions to physics@umich.edu. It's a particular pleasure to introduce today's speaker, Gabriele Carcassi, a researcher in the Physics Department and my collaborator. He's the lead of the Assumptions of Physics program, an interdisciplinary program working to identify a minimal, physically meaningful set of starting principles from which the laws of physics can be rigorously rederived. His research focuses on rethinking foundations of physics by beginning with physical assumptions and showing how the familiar mathematical structures of classical and quantum theory naturally emerge from them. His work spans physics, mathematics, engineering, and the philosophy of science. His background in scientific computing and software engineering has actually really contributed to the clarity and precision that characterize his research in the foundations of physics. He grew up in Milan, Italy, and got his degree from the Politecnico di Milano. In addition to being my collaborator, he also happens to be my husband, and we have two long-term collaborative projects that we've been working on together for 21 and 18 years, respectively, who are both here in the audience today. Please welcome Gabriele Carcassi.
So thank you everybody for coming. Thank you for the organizer, especially the one who presented me. And so let's get started with this. As you may know, does this work? Yes, it even works. This is a special year. It's in a year where we are celebrating the 100-year anniversary of quantum mechanics. And as you may know, quantum mechanics still has many mysteries. For example, who designed this logo, what it represents, and that's something that we'll never know. So what happened 100 years ago? 100 years ago happens that physicists saw that there were some problems with classical physics. And at that time, it wasn't classical physics, it was just physics. And what they found, for example, that they gave the wrong prediction for the black body radiation. That is, the spectrum of frequencies that comes from an object that emits light, like the sun. Or it gave the wrong prediction to the photoelectric effect in the sense that according to classical physics, it was about intensity, while in practice was about frequencies. And also classical physics predicted that atoms were unstable, that an electron would basically lose energy, would collapse on the nuclei, everything becomes neutral, and you can't basically have chemistry or anything. So that's kind of a bummer. So what happened then is that people got sort of preoccupied and started futzing around with matrices and waves, and so there were two different camps, and then the whole thing was resolved, and that's how we got quantum mechanics, which is basically a bunch of mathematical recipes that we use to predict and calculate things. So let's look at some of these mathematical recipes. I'll show you what it means to quantize a classical theory. So we're going to quantize a classical theory today. So let's take an equation for classical mechanics. This is an equation that tells us if we have a quantity f, and we want to study how it evolves in times, you have that the rate of change in time is equal to this object here, which is called a Poisson bracket. It's named after Simeon Poisson, who was a French mathematician, and if you translate his name, it would be salmon fish. So this is basically the fish bracket, the Poisson. Okay, so we have this equation from classical mechanics, whatever it is, and we want to quantize it. And we're going to quantize it according to the highly sophisticated Dirac's correspondence principle. So we apply this principle, and this is what we get. And it should be clear what's happening, right? We are removing the curly brackets, right? We are putting square brackets, and we are dividing by I, the mathematical, the imaginary units, and h bar, right? So let's do it again. This is another equation for classical mechanics. It's the Poisson bracket with position and momentum, so it tells you sort of the relationship between them. And now we're going to quantize it according to this principle. So what do? We remove the curly brackets, we put square brackets, and we divide by h bar, and this is what we get. Now, the next one, I want you to try do it. This is the relationship for angular momentum, right? This is basically Lx, Ly, and Z are basically the three directions of angular momentum, okay? And now you guys are going to quantize it by yourself with all that I taught you, okay? And I will show the answer, and if you're able to get the answer, please raise your hand to show everybody that you're able to quantize classical mechanics. Okay, ready? So who got it? Very good, guys. Right? So I see a young person there that raised your hand. No, he didn't. He just had the hand like that. Anyway, so you all guys are able to quantize a theory, and you might say, well, Gabriele, I don't quite understand. Like, I just substituted symbols. And that's exactly the point. Quantization is a formal operation. You substitute some symbols with some other symbol, and that's it. And you might think, well, you know, physicists are going to know exactly what those symbols mean. Not quite. What physicists can do is use those symbols to calculate things, which is handy. And so, for example, one of the things that you can calculate is probably you've heard about the Heisenberg uncertainty principle. So you have this sigma x that represents the spread over position, and you have the sigma p, which is going to be the spread in terms of momentum. You multiply these things, and this has to be greater or equal to 1/2 the expectation value of the norm, or the expectation value of this commutator, this square bracket thing that we saw before, and this was essentially h bar, and so you get h bar over 2. Right? So this is the type of thing that you do. Now, there are two things that I want you to be aware of the uncertainty principle. And for the first thing, I'll give you a hint. It's not about measurement. It's never about measurement. It's about preparation. So it's not that we prepare our particle and there is a secret, well-defined position and well-defined momentum, and we just really are not very good at measuring it, and so we have the uncertainty. No, it's like when it comes out of our preparation device, the position and momentum are not well-defined. Like, this is the core and important thing. And the second thing that you should know is that uncertainty is really a bad name. The real name should be indetermination, which is the original German, and it's also how it's translated in Italian and Spanish, for example. So what I want you to do for the rest of your life, every time that somebody talks about an uncertainty principle, you raise your hand and say, actually, it should be indetermination principle. Now, this is important because if you don't understand this, you're not going to understand other two features of quantum mechanics, which are contextuality and complementarity. Contextuality is really the idea that measurement cannot be thought as revealing as something that exists already there. They do something else. And complementarity means that for every quantity that you prepare well, you're going to destroy some other quantity and make it indeterminate. So these are the type of things, the type of history that we already have, they still have in quantum mechanics. And another one, which is also very popular, is the so-called quantum measurement problem, the fact that you have two laws of evolution. So if I give you a quantum state, and then I want to describe what happens during a physical process, I use what is called the Schrödinger equation, this thing here. And the important thing about the Schrödinger equation is that it's smooth. So if you have an initial state, it moves like little by little, right? And it's deterministic. If I give you the initial state, you are going to know what is the final state. And if I give you the final state, you're going to be able to reconstruct what was the initial state. So this is what you use to describe a physical process, but then doing a measurement, you have to do something else. You have what is called a projection, or also the collapse of the wave function if you want to be more dramatic. So if you have an initial state now, you're going to jump to a set of possible final state, which are the final outcomes of your measurement. And you're going to jump according to a probability distribution, so you don't know where you're going to jump. You're going to jump somewhere. And it's irreversible. You can't go back, because once you know where you jumped, you don't know what state you came from. Okay? And this puzzles people, and therefore what people do, ask what is quantum mechanics about, why we have all these weird things, and they try to create interpretation. Do we have hidden variables? Is it about agent information, all of that? Other people do something like quantum reconstruction. They try to find other different principles to sort of reconstruct quantum mechanics. So these are the type of things that people normally do in the foundations of physics. Now, since I'm not normal, and I'm an engineer, I don't care about this thing. What I care, I'm still stuck at the beginning, where classical mechanics failed. Because to an engineer, a failure, it's like wonderful. You get to learn. You don't want to cause failures, but you get to learn a lot of things from the failure. So my question is really, what is the ultimate reason why classical mechanics fails? Not why quantum mechanics works. And then how is it that quantum mechanics fixes things, right? So that then we can learn something from this. So this is the topic essentially of the talk, of the work that we're going to present. And since we saw that some of the failures are related to thermodynamics, are related to entropy and some of these things, we're going to look at the relationship between entropy and that uncertainty that we saw before in classical physics. So let's forget about classical quantum mechanics. Let's just look at classical physics and see what happens. So first I have to tell you a little bit what entropy is. So this is position, and this is momentum, so all the possible state configuration. And then you put a probability distribution of that. You could be here with different probabilities. So this rho is a probability density. And from this probability density, you can define an entropy by using minus the integral of rho log rho of this thing. Now, this might be a complicated expression, but actually it has a much simpler formulation if the distribution happens to be a uniform distribution over a region. If the distribution, the probability distribution is uniform over a region, you're going to have an area in terms of position and momentum. And this area, you can think it as counting states. And so you're going to put that this expression here, in this case, reduces to just the logarithm of the area. So the bigger the area, the bigger the entropy, the smaller the area, the smaller the entropy. Now, if you studied a little bit of physics, and you look at this equation, you're going to say, Gabriele, this makes absolutely no sense. Because the area here is measured in units of position and momentum, a product of position and momentum. So this number here has a unit, has a physical dimension. And now you're taking a logarithm of it. You can't take a logarithm of something that is a physical dimension. You can only take a logarithm of something that is a pure number. This is where physicists get a little bit sloppy. And I like to fix this expression because it turns out that fixing this expression is actually meaningful. So let's just stick a constant that we are going to call h for no apparent reason. And this constant now is going to have units of area of phase space, such that when I have an area and divided by another area, it's going to be a pure number, and everything works jolly good. And the physical meaning of this is that if I had an area, a distribution that has an area of h, then I'm going to have h over h, which is 1. The logarithm of 1 is 0, so the entropy is 0. So h is not just a constant that I put there to fix a unit. Well, that's what I'm doing. But it also has a physical meaning. It's exactly the area of phase space that would correspond to 0 entropy for a uniform distribution. So now that we have fixed the equation so they are physically meaningful, like the physics actually work because it wasn't working before, we can now plug them in and plot the entropy versus the uncertainty. And you get this graph. So on this side, we have the uncertainty measured on units of h. And here we have the entropy. And what you see is that there is a region white here where all the distribution, the classical distribution, can exist, but no distribution can be here. So you're not going to have a distribution that has this uncertainty with this entropy. Because what happens is that you have something called the Gaussian bound. If I fix an uncertainty and then I go up and increase the entropy, at some point I hit the Gaussian distribution, and the Gaussian distribution is the one that maximizes the entropy for a given uncertainty. I can't go farther, more than that. And so now if you look at this equation, you kind of see that there is a sigma x and sigma p here, there is a greater or unequal, there is an h. It kind of looks like the indetermination principle that we saw before. So what you do, you exponentiate, you put things around, and this is what you get. Sigma x, sigma p has to be greater or equal to h over 2 pi e, the exponential of the entropy. And this h over 2 pi, like mimicking what you do in quantum mechanics, you just call it h bar. So now you have this thing, has to be greater or equal of h bar over e. What basically means is that if we take a point and we minimize the uncertainty, at some point we're going to hit the Gaussian bound, and we can't get the uncertainty less than that. So what basically this tells us is that the entropy puts a lower bound on the uncertainty, but it's specific to a particular distribution. Like the uncertainty, the interpretation principle that we had before was something like more like a law of physics. All distributions have to obey that. So we need some type of universal lower bound on the entropy. And so you think, where can I get a universal lower bound from the entropy? Well, actually, you can get it from the third law. The third law of thermodynamics has many ways of being stated, but there is this one. Every substance has a finite positive entropy, but at the absolute zero of temperature, the entropy may become zero, and does so become in the case of perfect crystalline substances. And by the text, you can see that it was written a while ago. So the point is that if the entropy has to be greater than zero, then the product of the uncertainty has to be greater than h bar of E. So what we basically have here is a classical uncertainty principle. Any objection? Well, I'm a very disappointed guy. It should be indetermination principle. Okay, so we got this. And now we can compare the two theories. We can compare what we have in classical mechanics. We have h bar over E, which is a little bit more than just 2 that we have in quantum mechanics. So you can sneak up a little bit more, less uncertainty in classical mechanics. So you see, this is the Gaussian bound for classical mechanics. And here in red, I don't even know if you can see it, this is the quantum one, right? And you can see that they quickly become very similar, with just few units of uncertainty. And the other thing that you should know that the entropy of quantum state is already negative, so you don't need to add the extra exclusion. The quantum entropy is already non-negative. It's already incorporated in the theory. So the picture that you get is that quantum mechanics takes the third law seriously. Like it's there in the theory, you can't take it out. Classical mechanics, like, well, do I really have to follow the third law? I mean, and so you need to cut it, after the fact. And so I was looking at that years ago, noticing that, again, at high entropy, things become very close to each other. And I thought, well, wouldn't it be nice to say that the quantum mechanics recover classical mechanics at high entropy, right? The theory are different at low entropy, clearly, but at high entropy, they become very similar, it seems from this plot, right? So if I have a state that it's a high entropy in quantum mechanics, maybe I can just fudge it and say, yeah, it's a classical state, and I'll use classical mechanics instead. And I had this conjecture for a long time, and I tried to, at conferences, discuss with people that could help me because there were some parts of that I didn't know how to proceed. And I couldn't find anybody. Then I got fed up, and I did what every strange person would do. I posted a video on YouTube. And even stranger, a month and 10 days after that, I got an email from an atomic experimental physicist that said, oh, yeah, actually, you could do it like this. And then after 6 months, we had a paper out. Now, the paper is still under review, but the reviews are positive. We just have to go and address all the comments. So what is this? How does this work? Again, we have the graph that we had before. And you imagine to take all of the probability distribution of the mixed state at a particular level of entropy. And you want to find a transformation that increases the entropy of everything, but leaving them all at the same level of entropy. So you take something and you slowly put everything up at the same time. And if you do that, what this transformation has to do, if you remember those square bracket thingy before, you start with something that has 1 here, and you apply the map, you need to have something that has lambda, that it's a constant such that everything sort of is spread in the same way. And if you remember, this is exactly what happened when we were calculating the indetermination principle, and so we are going to have something h bar over 2 lambda, again meaning that we are spreading out all this distribution and we are increasing the uncertainty. And so since the uncertainty is increased, yeah, the quantum effects might be there, but since they are so confused in this higher uncertainty, you're not going to see them. And so you're not going to see them, since the quantum effects you can see them, you might as well classical mechanics. And this is how it works. Very simple. Now, this is a way to do the limit, but mathematicians have a different way to do the limit from quantum mechanics to classical mechanics. They take this square bracket thingy, they take h bar that goes to 0, and they can show, because these are not just numbers, so this is not just going to blow up to infinity, they are going to be able to show that this recover the curly bracket thing, the square bracket thing. So you can see that this is kind of an inverse of the Dirac principle that we had before. And this is great because mathematicians can use it and make approximation, and you can study these things. This is all great, except for one tiny problem. And it makes no physical sense. Because h bar is a constant, and what does it mean that we are taking the constant to 0? We are changing the universe such that, no, it doesn't make any physical sense. But this is what mathematicians do. Now, the cool thing about our limit is that we can reframe it such that we get the mathematical limit. So instead of saying, OK, we have a state we go at high entropy, we take the pure states, the ones that are 0 entropy, and we bring them down. Because, relative is the same. I can increase this and go up, or I can decrease the everything and go down. So if you do that, that lambda that appeared on the right side becomes the inverse, becomes 1 over lambda. And now you can take that lambda, put it inside here, and now you have h bar over lambda here, where you just have h. And now if you take lambda that goes to infinity, this becomes bigger, but h over lambda is going to become smaller. So it's not that we are taking really h that goes to 0, but we take h over lambda that goes to 0, and then we recover our nice Poisson bracket, and the fish are happy. Okay? And this is great for me because it basically puts the classical limit of quantum mechanics in the same vein of the non-relativistic limit. If you have already seen this picture, you basically get the sense that, okay, you have relativistic mechanics and that you need it when you are going at high entropy, at high speed. But then if you're at low speed, you can basically say, well, I can just use non-relativistic mechanics, so the mistake that I'm going to make is not that much. And again, mathematicians have a different way to express the limit. Instead of saying, oh, I'm at low speed, I take the speed of light and I say that it's infinite. Which, of course, makes no sense, except, if your speeds are low, your speed of light is very high, so you can pretend that it's an infinity. So it's a way to rephrase the physical limit in a way that it's easier to start when you're doing group deformation and the things that mathematicians like to do. And now we have the same thing for the quantum and classical limit. We are at low entropy. Of course, we have to use quantum mechanics. Then we increase the entropy. Well, there's so much uncertainty that we doesn't care. We can use classical mechanics. Or if you're a mathematician, you can just say, oh, I'll take h bar and let it go to 0 because I prefer it that way. And the thing is that there is no mechanism in either way. Like in the foundation of quantum mechanics, a lot of people try to find some mechanism of which, after that, you get classical mechanics. And if you think about it, when you're making the non-relativistic limit, you say, am I at low speed? Nobody asks you, why are the speed low? Like, who is trying to push my spaceship so that I'm still at low speed? That doesn't happen. It's just, it doesn't matter. As long as your speeds are low, you're going to get the non-relativistic limit. So now it's the same thing for classical mechanics. We go at high entropy. how do we get to high entropy? Well, we could have a thermodynamic system that goes at high entropy, having high temperature, or there could be entropy production from the environment that people do in the coherence, or just our preparation devices are so bad that when they prepare a system, there is so much uncertainty that we are at high entropy. It doesn't matter. As long as we have a high entropy, we can get the classical limit. So a lot simpler. So now we have this situation where we saw that we can do the quantum to classical limit by taking the square bracket and going to the curly bracket by doing the entropy limit. But we still have the problem that what is it that we were doing when we were doing quantization, where we were substituting the curly bracket with the square bracket. We were kind of just be tempted, oh, it's just the inverse thing, but we kind of have to prove it. And so we have to ask a mathematician to help. And mathematicians say funny things like, up to isomorphisms, the Moyal bracket is unique one-parameter Lie algebraic deformation of the Poisson bracket. And so you kind of have to translate this, but what does this mean? Well, it means this. If I ask for a theory, I start from classical mechanics, and I ask for a theory that puts a hard lower bound on the entropy and recover classical mechanics at a high entropy, there is only one way to do it. Because up to isomorphisms, this is the only way that you can do it. So we can say that what we are doing when we are quantizing a theory is really just putting a lower bound on the entropy. Quantize a classical theory means putting a lower bound on the entropy. So now we can know what all those abstract formal procedure are actually doing. Now, do I know how every single quantum effect can be derived from the fact that we are going to have a lower bound? Currently, no, it's part of what we're still doing. But you see, the nice thing about mathematics is that you can now be certain about things that you can barely understand. So you that tells you, yeah, there's going to be something somewhere that is going to make this thing work. So, okay, this is the thing that works, but what does it mean physically? How do I show the picture, the difference between these two things? Well, so imagine that you have a ball, right? And I can take the ball, you can throw the ball and study the ball and how it goes. But you can also take a red marker and make a red dot on the ball and study the motion of the red dot. And in classical mechanics, you're assuming that you can make that red dot as small as you want. And studying all the potentially infinitesimal red dot on the ball is the same as studying the whole ball. And we say that the system is infinitesimally reducible. You can study the whole, or you can study these infinitesimal parts. That's a classical system. For a quantum system, well, you can imagine that you have an electron, and you can study the electron, you make it do things. But you can't take a red marker and mark a part of the electron and say, OK, let's interact only with this part of the electron. It doesn't work like that. Either you interact with the whole electron, or none of the electron. So you can't get information about the parts of an electron. And so that system is irreducible because you don't have access to internal dynamics. That's what the lower bound on the entropy means, and that's what a quantum system is. And note that whether the internal dynamic is accessible or not, it depends on the context and depends on the experiments and processes that are available to you. So, for example, you could have a proton, and as long as you are not able to probe what's inside the proton, you don't know what the internals are doing. Well, that's going to be irreducible. That's going to appear like a quantum system. So we can treat proton as a single particle, and they're going to diffract and interfere exactly like an electron does, just with different parameters. Same thing for an atom, same thing for a molecule. As long as all our processes are not going to probe what's going to be inside, then our system can be assumed to be irreducible, and you just use the same model. But if tomorrow you find a way to break up the proton and see what's inside and so on, then you can't say that it's infinite, that it's irreducible, there is going to be substructure, it's not going to be a single quantum system anymore. Right? So it's all about what assumptions can be taken at a particular time to model the system that we have. Okay? So that's what basically is the gist of all this. But So it's all about the entropy, and it's all about putting this lower zero on the entropy. So if we really want to understand all of this a lot better, we have to answer two questions. What is the entropy, and why do we need a lower bound? Now, the first question is a little bit tricky, because von Neumann famously said nobody knows what the entropy is. And so if you look in textbooks, you're going to find something like, oh, you can think it as disorder, you can think it as information, and then you find other textbooks that say you can think of lack of information. These two guys hate each other. But the problem with all these things, they are all like, oh, yeah, they're in this context. They're never telling you exactly what the thing is. It's like, it's analogies. I don't like so much the analogies, because you don't get to understand what thing is. In the word of the great philosopher, is or is not. Right? You have to tell me what things is. And unfortunately, in physics, a lot of the time, we get these vague explanation because we're in a rush, and then we want to do other things, and then the vague explanation that we have at the beginning remains there for centuries, and we never know what we're talking about. So in our project, we try to go and drill more and say, okay, what are clear starting point? And we're going to do it for the entropy. What is it that the entropy is describing? What is it that it's the minimal requirement that we need to be able to define this, this quantity? And this is what comes out. So suppose you have a possibly infinite collection of things. Like these are collections of things. And you want to ask, what is the variability inside the collection? How different or how similar are they from each other? So in the top left here, you can see this set is pretty much very homogeneous. Yeah, there are a few things, but it's mostly circles. Come on. The thing in the middle, well, there is a little bit more variability, right? There even are different things that weren't there before, but it's still, it's like more than 50% are still circles. And you see here instead, this is a lot more variability, right? If you had to get one at random, it's a lot more stuff. So that's the intuition, right? Okay, but now we have to make it precise, right? It's not enough to just say, oh yeah, variability. No, we have to make it precise. How do you make it? Well, as an engineer will tell you, need requirements. So you get a distribution. If you have a discrete distribution, whatever it represents, it might be a statistical distribution because there are actually lots of molecules that are in different states, or it's a probability distribution, or it doesn't matter. As long as you have a distribution, you want to say, I want an indicator that tells me how different are the elements of the distribution from each other. And you will want these three things. You will want it to be continuous, meaning that if you change the distribution a little bit, the variability has to change a little bit. It can't change a lot. So it has to be continuous. It has to increase if the number of cases increases. So if I have a uniform distribution and I stretch it to more cases, the variability increases. Okay, it can't go down like that. And it has to be linear in probability. What does it mean? That if you imagine that you have your distribution and you chop it in half, the total variability is going to be the variability of choosing which distribution part of the distribution I am, plus the average variability in the two halves. Right? And so this is the mathematical expression of that. And it turns out that these are just like a retelling of the starting point that Shannon used for his information entropy. It's just that they're set logically in a better, more general setting. And you can show that under this assumption, there is only one choice, and it's this p log p, like the rho log rho that we had before. So by saying I have variability, the main indicator of variability has to have these properties, you get this, and this can be generalized to both the continuum and classical mechanics. So now I can say that entropy is variability, because I started by knowing what it is. I didn't start with some equation. I started with, this is what I want to describe. These are the things that this thing has to describe. And so I know that every time that there is an entropy, there is a variability. Now, are other people agree with me? Well, let's see. This is our paper that we published in 2021, and these are a sample of papers that actually cite our paper. And let's look at the variability here. This one, why so slow? Model of Parkinsonian Brady, I don't even know what that is. It's from Nature Review of Neuroscience. And this one is from analysis of behavior, experimental analysis of behavior. This is from logistics. This is geophysical research, modeling Earth systems, and so on. So I have a lot of variability in my citation, which basically tells you, yeah, this is what this quantity is. And you can imagine that if you have high variability, right, you can kind of think that there is more disorder in some sense. And if you have higher variability, well, you're going to need to tell me a little bit more information to pick which element you're picking, because you're choosing from a wider selection of things. But sometimes you just have an island with some animals, and you want to know how varied are from each other. And in this case, there is no disorder, there is no information, there is just variability. And this is why this concept is so widespread, because the variability is something that's everywhere. So, okay, so we finally know what entropy is, which is a plus. And one of the things that is important is that it's not a property of the element, right? It's a property of distribution. So if you just have an element like this and you say, what is its entropy? Well, you say, okay, what is the distribution? Just to be clear, for example, if you asked me, what is my probability of being blonde, right? That doesn't make much sense. If you asked, what is the probability that a person born in Italy in 1976 is blonde? Okay, you're going to have a probability. But you can also ask, what is the probability that a person in the United States is blonde? You're also going to get a probability, and it's going to be a different probability. I am a member of both populations, so the probability is not my property, it's a property of the population. So in the same thing here, the entropy is a property of the distribution. We assign entropies to distribution, so when we have states, those states are, in some sense, distributions. And here's the problem. Distribution of what? Right? We need to clarify that, because otherwise we don't know what we're talking about still. So you could say, like Boltzmann did, for example, you have the gas, we have lots of molecules, they're distributed in position and momentum, you calculate the entropy based on that. And it turns out that that doesn't work. So it's not really a distribution of a statistical distribution of states. You can think like people do in quantum Bayesian interpretation. It's a credence distribution. It's like what an agent, a rational agent, would think that things are. And that's a way to get distribution, but then you have a problem that the distribution is not objective. So I have my distribution, you have your distribution, the other guy has a distribution. And what does it mean that we do physics and we are all thinking different things? That doesn't work. And then there are lots of other people that say, aha, it's a probabilities distribution of the outcome of measurements, because at the end of the day, physics is about measurement. It's not about measurement. It's never about measurement. It's about preparations. Okay, so the entropy is the variability of an ensemble, which is the collection of all outputs of a reliable preparation procedure. So you have a preparation procedure, something that you have in a lab, right? And then you can push a button and prepare a bunch of things multiple times. And then every time the thing that is being prepared is not going to be exactly the same, right? There's going to be some variability. So you take all those possible outputs, put them together. They are an ensemble, and they have variability inside. So that's what physics is really describing. And one of the problems here is that this sort of goes a little bit counterintuitive, because a lot of people have this picture of physics, that physics describes the evolution of a particular system like a movie, that you have, let's say, a position in terms of time. And so you're going to see that at each instant of time, you have a picture, and you're going to see that this is going to roll down because the position is going to change. And this is the picture that a lot of people have in their head. And this picture does not work. No. Physics describes the evolution of similarly prepared systems, because the laws of physics are of the type, every time that I prepare a rock with this slope and so on, I will get these things. So it's not about a single instance of the film strip. It's about an infinite collection of pieces of film strip that you're putting together and putting them on top of the other. So if you look at a single frame, what you're going to see is this blurry thing, because you're taking an average of infinitely many possible things. Okay? And this is what we actually do. So whenever we have an X here, even in classical mechanics, you should think that this is a statistical description of preparation and measurement outcome. It's not one thing, it's every time that I do the same thing. And even T is the statistical description of all clocks that are synchronized at a particular event. Because, for example, how do we define a UTC, the Coordinated Universal Time? How do we do it? We have a bunch of metrology labs around the world. Everybody has their atomic fountain clock. They tune a laser, and they define their clock. And then all this data is aggregated by some guy that is going to discard the outlier because clearly those metrologists didn't know what they were doing, and then take the average of all the clocks. So even the clock that we have, that we define experimentally, is literally a statistical description. That's what we do. And so in physics, the point is that we can only study relationships that can be reproduced, right? Things that you can always do it one more time. And once you have something that can be done one more time, you're assuming that you can do it infinitely many times. And now the relationship is about these ensembles that are prepared infinitely many times. And so now we can know what the entropy is. It's about an ensemble. But you might say, yeah, OK, fine. It's about these ensembles. But still, on the single instance, I will have one frame. And so I'm going to have distribution on this frame. You still need to tell me what these things are. And that's a fair point. But if you look at this frame closely, it's not about an instant in time, because the frame has a shutter speed, and is going to be taken as an average of how much the shutter was left open. So even a single measurement is an average over a finite time. When you measure temperature, you're going to have a thermometer. You have to stick it there for a finite amount of time to get a reading. Right? So even these things are not really single things. They're ensembles themselves. To put it a little bit more clearly, hopefully, so to be able to define the probability distribution over heads and tails, you first need to tell me what heads and tails are, and heads and tails can't be distribution of heads and tails, of course. That doesn't work. But we can do that. We can define heads and tails, because if I leave the coin on the table, it stays heads or it stays tails. If it kept flipping more than 100 times a second when I put it there, I wouldn't be able to know whether it was heads and tails. It would just be a complete blur. So the point is that even when we have a state of the system, we're describing the system at a particular time, well, the state is what remains stable for at least a short duration of time. And so depending on the system, part of the definition of the system is to define all these, what is the critical time, and what are all these properties that remain stable for those times. So even the state themselves are ensembles. So you have essentially ensembles of ensembles of ensembles. It's ensembles all the way down. OK, so we answered what is entropy. Entropy is about the ensembles of preparation that are ensembles of ensembles. And now, why do we need a lower bound for this thing? Well, so again, let's compare classical mechanics and quantum mechanics. We imagine that we have a preparation procedure. The assumption in classical mechanics is that we can make this preparation procedure always more and more and more and more and more precise. At some point, we can have perfect preparation. Like we have a procedure that always gives me the same position, the same momentum at infinite procedure, and I can think of any other preparation as just a statistical mixing of all these things. I put them all together, and then I take the output, I mix them, and I get. That's basically the assumption that you have in classical mechanics. The problem with that is it's completely unrealistic, because we can't do that in practice. And while we can do it in practice, then that's what quantum mechanics is telling me. Look, it concedes that there are no perfect preparation. And why are there no perfect preparation? Because we don't have the control over the whole universe. Because if somebody on Andromeda is moving their furniture and is creating a gravitational wave, we don't have a way to block that gravitational wave, so it's going to just slightly interfere what we're doing, and then everybody in the universe is moving at the same time, which is very annoying. And then you're going to have you're going to have that interference in your preparation. And so that's something that we cannot do. But the fact that we cannot do it means so that it can't be done. So it's not that, oh yes, secretly it's done, but no, it's like it can't be done. So whenever I'm linking the preparation of one device with the outcome of a measurement, I cannot have a map that maps the single instance here to the single instance here. I can only map the whole distribution to the whole distribution, and I can't know what these components of the distributions are doing. So that's why we have this lower bound of the entropy. Another way to look at that, which kind of connects to the way that we looked at entropy before, we saw that entropy was the logarithm of the count of states, right? So this A over H was the count of states. And we saw that if A was H, then this was 1, and this was 0. So it means that if we have one state, the entropy is 0. But if the entropy is less than 0, then we're basically saying that there is a region in phase space that has less than one state. What does it mean for something to have less than one? Either you have a state or you don't have it. It doesn't make any sense. So saying that I have a lower bound on the entropy, it's like saying I have a lower bound on the number of states, and I better have at least one state. And so now we have these two things that are sort of, explained. We understand what it is, and if all the math checks out, then we know that any effect that we have in quantum mechanics has to be the consequence of these two insights. Okay, so this is where I'm going to go a little bit more on the technical detail to, again, try to re-understand this idea of counting and how is it that quantum mechanics sort of changes it. And this is part of a result of a project that was funded by the John Templeton Foundation. And so the idea is that suppose that you have your space of states, and that is a continuum. You would like to have something that is called a measure, that you give it a set, and it tells you, how many states do you have in this set? So, for example, here in this sphere, I have this region of U. I give you U. How many states are there in U? And you would like this mathematical thing to have 3 properties. You would like that if you gave it a single element, you give it A, B, or C, this would tell you 1, because there is one state. But you would also know that if I have a finite region, like U is a finite region, I would like to have finitely many states in this region. And then I would also like that the count is additive to joint states. So if I have 2 sets and they're not overlapping, the number of states in both, it's the number of states in one plus the number of states on the other. Now this intuitively, if we want to count, we would expect these 3 things. And the problem is that on the continuum, these are incompatible. Because if I have a finite region, it's going to have infinitely many points. And if every point is 1, then I have an infinite measure on there. I have infinitely many points. So that's not going to work. What you have to do is you have to pick 2 of them. You have to disregard 1 and pick 2. And coincidentally, if you remove the middle one, so you say, OK, every state counts on 1 and I'm additive, you have the measure that you use in classical mechanics for a discrete system. Like I have 1 particle, 2 particles, 3 particles. That's a discrete variable, and that's what we use. If you remove the first one, you have what is called the Lebesgue measure, which is the thing that you were doing before, delta x by delta p, right? This side times this side is the area of this region. But then, of course, if you have a single point, it's 0 times 0. So the point is not worth 1. The point is worth 0. What quantum mechanics needs to do instead, then, is to remove the second one. The count has to be not additive. So if you imagine that the whole sphere is finite, and every point is finite, as you go closer and closer, like the whole sphere is actually worth 2 in quantum mechanics, and then when you go, it has to converge to 1. And so if you have multiple points, you are not going to have this additivity. And so this is part of the thing that we're trying to understand, whether these things can be generalized. But this tells you, like very quickly, why, in a lot of ways, quantum mechanics is intuitive, because we're counting in a way that we wouldn't expect. We're counting in a way where if I have 2 sets, like the whole set is not just the sum of the 2. OK, so we saw that thinking about entropy and clarifying all these things makes us understand how classical mechanics failed. We know why it's failed now, because it didn't have a lower bound on the entropy, and we know why quantum mechanics fixes everything, because it goes and puts the thing there, right? But if you're an engineer and you study failure, the point is to not repeat the failures again, right? So can we use similar arguments to understand why quantum mechanics at the end of the day has to fail, and why we should do something different to make quantum mechanics and general relativity compatible? So to do that, I need to tell you a little bit of what a field theory is, because general relativity is a field theory, and so far we only talk about particle mechanics. Particle mechanics works like this. So the state is defined by all the variables of position and momentum, right? And so you have like 6 variables for each particles. You're going to have 1 billion particles. It doesn't matter. It's still a finite number, very large, but still finite. For a field theory, instead it's different. You have a field, and a field is at every point in space. So you're going to have a value for the gravitational field here, a value for the gravitational field here, and so on. So you have infinitely many, continuously many variables. How do we count them? How can we count how many variables do we have? Because you might not know that, but there is a problem in counting on the continuum, right? We would like to have a region of space and get a map that tells us a volume that is proportional of how many variables are there. And we would like that every point says, oh, I have 1 variable at every point, and at every finite region, I have finitely many variables, and I would like the variable to be added, and then again, I have the same problem. I can't do it. So again, what I need to do to solve this problem is sort of have a non-additive measure on the volumes of space, such that I can get the first and the second, and I have to remove the third. So essentially, what this should tell us, in the same way that quantizing a classical theory was about putting a lower bound on the number of states so that I can always say I have at least 1 state, it seems to me that quantizing space-time means putting a lower bound on the number of variables, on the number of degrees of freedom. And in the same way that a region of state space with less than 1 state makes no sense, and it gives rise to quantum mechanics, we should be able to say that a region of physical space with less than 1 degree of freedom makes no sense. So again, if you imagine that I have a ball in physical space, right, and there are going to be some number of variables in this ball, if I imagine that to double it, right, on a large scale, I would imagine, okay, I'm also doubling the number of variables that I need to describe. But the idea is if I make it smaller and smaller and smaller, right? You know, I start linear with the radius. I go smaller and smaller and smaller. At some point, I can't go to 0. I have to go to 1. So I have to have that no linearity over there. I have no idea what is the right math to do this. I really don't know. In fact, I don't even think we have the right math to do it. But it's even worse than that. I don't even think we have the right math to specify the problem. Because even though this makes sense sort of intuitively, when I write it down, I have inconsistencies. And the fundamental problem is that, unfortunately, the way that our current mathematical theories are defined are not really well specified mathematically. Like, there are some things that the mathematicians would like, right? And in physics, we still use things that are mathematically defined because, again, we want to just get a result quicker. So whatever works, works. And even if a mathematician complains, whatever, it's a mathematician, who cares? And this attitude is really encapsulated by this quote from Sabine Hossenfelder in Lost of Math. She says, but we don't develop theory by writing down assumption and then derive observable consequence in a sequence of theorems and proof. Oh, we're not interested in looking at what the assumptions of physics are. What happens is that in physics, theories always start out as a loose patchwork of ideas, and then cleaning up the math that physics generate in theory development, you know, those rascal physicists, and finding a universal assumption from which the whole theory can be derived, is often said to our colleagues in mathematical physics, a branch of mathematics and not physics. And I can tell you how much this attitude is idiotic, and I know because I used to have that attitude. I was an idiot too. Until at a math conference, I was, after presenting, I was talking to a mathematician there about these problems. He looks me in the eye and says, look, I don't know physics. I don't know what you guys need. And the thing that I never realized before that is that math is not just a tool for calculation in physics. So in physics, you write a Python code to make some prediction or calculation. You can throw away the Python code. You still have the result. You haven't lost the physics. If you take a physics theoretical book and you take the math out, well, there isn't much left, right? Math is really the language that we use to specify our theory. It's not just a tool that it's not important. And at the end of the day, it's up to the physicist to develop a clear physical model. So in the end of the day, it's up to the physicist to know what math is appropriate or not. The mathematician can help, can tell you, oh, look, you have a problem there, this is not a consistent. You could choose between these things. But then, if the physicist ignores the mathematician, it's certainly not the fault of the mathematician. And so the whole point is that having a clear physical model means going through all that math and understanding, okay, what is the topology represented? Is this the right topology? Oh, I have infinite dimensional mathematical spaces. These have these problems. Okay, well, you need to be competent in all of this to be able to then get a clear physical model. So this idea that you can take something hodgy-podgy, you give it to the mathematician, he's going to make it precise, and then you take an interpretation or a sprinkling on top and you're done, right? That's never going to work. Because if you ask any engineer, he will tell you that big systems that work always come from small systems that work. They never come from big systems that don't work. So all this property, precision, rigor, meaningfulness, it's not something that you can add after the fact. You have to grow them from a small set of ideas. And so the point is that if we want to have a foundation of physics that is physically meaningful, mathematically rigorous, and philosophically consistent, the only way forward is essentially to go back and reconstruct everything, every single mathematical object, every piece of a physical theory, from a minimal set of physically meaningful assumptions, and this is the goal of our Assumptions of Physics program. Thank you for your attention.
Thank you very much. We'll take a few minutes for people who need to head out, and then we'll start our Q&A. And as a reminder, those following online can email their questions to physics@umich.edu.
Thank you.
Just a little bit. There we go.
All right, let us start with our questions. We've got the first one here in the room.
Hi, that was a wonderful talk.
Thank you.
I had, I guess, a couple of problems with that part about the 3 countability criterion.
Mm-hmm.
And I guess that's just because I come from a field that uses a lot of density functional theory. Are you familiar with that?
I'm afraid not.
Okay, that's basically, you basically collapse your wave function into a bunch of densities for an electron around an atom.
Mm-hmm.
And with that, you actually, I guess, when you're doing it in a computer, right? if you get a space that's small enough, you eventually get points where you can describe a little bit of a variable, but it's not enough information to be able to describe one entire variable. So I think you mentioned a couple slides back that as your space goes down and down to 0, it should collapse into 1. It should collapse into just describing a single variable as opposed to no variable, right?
That's for a field theory.
Ah, okay.
Yes. So the idea is that if I imagine that I have, let's say, the electromagnetic field here, right? At every point, I will have a set of variables, right? And the classical assumption is that if I take a volume and I chop it in two, I need half as many variables, to the point that when I have a single point, right, I don't have a distribution anymore. Like I have a measure 0 set.
Yeah.
So the point would be, like the corresponding idea is that, how can I put it? What you would like to basically say is that the volume in space, actually what it's counting, it's the number of independent variables. So the things that you can specify independent from each other. So if I have 2 points that are very far apart, I can put whatever field I want here and whatever field that I want here, I'm still fine, right? And so if you under that assumption, and the classical assumption, no matter how close these points are, they're still independent. Even if they're an epsilon away, they're still independent. The idea of putting a quantum measure would basically saying, no, that doesn't work like that. At some point, I will have a scale, right, in which I have 2 points and I have 2 variables, but those variables are not independent anymore. So if I look at a small region of volume, right, I will have like 1.5 independent variables because that's the amount of information that you can get. I need to specify less and less information because all those variables are going to be highly correlated. Now, if you are in a classical theory instead, you have the electromagnetic field, you can have your, as high frequency as you want. So even in a small region, you still have to tell me infinitely many things.
Okay, I think I get it. Thank you.
Okay, good.
I have a question, actually. So could you say a bit more about how the zero lower bound on entropy relates to non-locality in quantum mechanics?
Okay, so imagine that you have my position and momentum, like classical, right? And I have a distribution, right? And we saw before, a lower bound on the entropy means I can't just have like a single point. I need to have a distribution with a minimum uncertainty. So if I have a distribution with a minimum uncertainty, right, then it means that my state has to be distributed in space. So already that tells you that a lower bound on the entropy, even if you're just in classical mechanics and you just fudge this cut, you're going to have a finite distribution in position, and therefore your state, your distribution, is non-local. And again, it's not weird because it's a distribution, and it's a distribution of these multiple preparation, and each match preparation is in a time step. So it's a distribution of, it's not a mystical distribution. It's just a distribution of the preparation.
So the idea that you can't interact with just a piece of the electron, a bit of the electron with your red marker, you're interacting with the whole thing, or none of it. Another question in the room?
Hello, thank you very much for that. Thank you very much for that talk. That was very thought-provoking and interesting. So when we were talking about entropy and kind of like different perspectives on entropy, I remember you briefly mentioned a kind of like Bayesian interpretation, whereas about a rational, like what a rational observer would know about a system.
Mm-hmm.
I guess I was kind of curious because you talked briefly about like that, like if we were to accept that perspective, that would sort of be losing objectivity in like our statements about physics, but aren't a lot of statements in physics very observer dependent? So stay like with relativity, it's very like different observers are going to perceive things differently based on speed. And I guess like more generally, when we make statements about science, we are coming from an observer perspective of ourselves. Like how, I guess I'm kind of curious like how that, like the interplay there between like the
So
fact that we do
there are many
observe this.
questions hidden in the same question. So
Yeah.
first of all, the notion of entropy is completely general, and of course it applies in the case of agent information, as I said, also in statistical things. So the entropy is a variability of a distribution regardless of what that distribution is. So if I have I could have a bag of balls, right? And there is an actual fraction of balls, so there is a variability of what there is, right? I could pick one ball at random, and then I would have a probability, and now it's the variability of what I could pick, right? Or I have my agent information. I think that there are these many balls inside here, right? And I have a credence. And then it would be the variability of what I think is there. So you could have the variability of what is there, the variability of what could be there, or the variability of what you could think is there, right? And that means that the same concept of variability can be applied to all these things. And so the people that do, I don't know, ecology, it's more of the variability, what is there. In physics, a lot of the time, it's a probability. So probability of could be there. And when you're doing LLMs and all the, a lot of language models and so on, it's a probability, it's a credence distribution. So it's not a problem that you can have these three different things. The problem is identifying what is your distribution about in the specific context so that you don't get confused, right? If in physics, the probability that we get from statistical mechanics by entropy maximization, right? Like for people that don't know, statistical mechanics works like this. You have a state space of how the system could be configured. And then you have some constraint, so a particular type of energy, a particular set of values. And then you find the distribution that maximizes the entropy according to those constraints. And those are the distribution and then you find experimentally. So if I said, well, what I'm maximizing is the agent information, or something like that, how is it that everybody seems to have the same information and finding the same thing? It's kind of fishy. So, of course, you can interpret any probability at least as agent information. This is what De Finetti's argument was. Even if it's the probability of what is there, I still have to think that it's what is there. So even a probability of what is there is also a credence. That's fine. But if it's the probability of it that it's there, it means that we all are going to have the same credence, and the experimental results are not going to care of what my credence is. So if I have a procedure that gives me an objective probability distribution, then everybody goes and measures and finds the same thing. You can't say, oh, it's just a credence. No, that there is a physical process that is constructing the distribution, and you're looking at the output of the physical process. Now, the third part of the question was, oh, but in physics we have things that are depending on the, on what type of experiment that we do, or the reference system that we have in relativity and so on. The point there is that there is still something objective, and everybody can map whatever they think are going to get to each other, right? So it's not that there is no single thing and everybody have a particular perspective. It's like there is a statue and just looking at it from two different sides. The statue is still there, right? It's not like a credence that, the lights is off, I think there is a particular statue, and somebody else thinks that there is a particular statue. That's a different setup.
Okay, thank you very much. That was insightful.
Go to a question online. What is the size scale when the world, i.e. measurement, looks more quantum versus when the world looks more classical? So a question about the size scale of quantum objects.
Right, so it's not a problem of size. If I can go back, I don't know, can I go back to this diagram? Where is it? Oh, so many. Can I go? There you go. It was right. Sorry, this is taking. There you go. So if you see in this diagram, a lot of the time, people on these axes are going to put size. Size is the wrong thing. Like there is no minimum size for entropy. We have experiments that shoot photons to a satellite and then bring it back, so it means that they go kilometers away, you still keep the entanglement. So it's definitely not about size. And it's also not about number of particles. You can have what's it called? A Bose-Einstein constant state, which is basically a quantum effect where you can take a bunch of atoms and compress them to the single state, and they behave like I don't know, superfluid. I don't even know how to describe it. There's a special quantum state, and it's very, very quantum. And again, you can do those things now that are kind of macroscopic with like very, very many number of molecules. So the quantumness is never about size, and it's never about number of particles, even though in some cases, that's a good parameter. But it's a good parameter in those cases because it's a sort of a foreshadowing that you're increasing the entropy. So you can have a quantum system that is as big as you want as long as you're keeping the entropy down. So if you think about, you have superconductors, again, those are quantum effects. Why are they easier to perform at a low temperature? Because at low temperature, you have low entropy. And if you want to have a higher temperature superconductor, you will find that a lot of the time, they put high pressure. Why the high pressure? Well, because if you are at high pressure, you have low entropy. If you want to create one of these Bose-Einstein condensate, what do the people do? They have to take all these particles and shrink them in a very small region of phase space. But a small region of phase space is low entropy. So the cool thing about this result is that you can go in a lot of these places where you wonder, oh, why do I have a classical system or a quantum system? And in all the cases that we have identified, that there is always, it could always be translated in entropy. Now, of course, saying all of them are like that, it's difficult because, I'm not going to have the time to look at all of them, probably not in a lifetime. But the point is that's where you have the math. And the math tells you, OK, this is equivalence to do the h-bar limit. The h-bar limit is going to be the thing that gives you classical mechanics. And so that's what gives us confidence.
So a neutron star would be a good example of a large physical scale and very high temperature, but very high pressure because of the gravitational forces. A neutron star behaving as a quantum object, or clear quantum phenomena.
I always forget astrophysics.
Yeah. Okay. Question in the room.
So I had two questions. The first one was about the T operator that you had in the very first one, this entropy increasing operator, and I wondered what exactly is this operator, and is it reversible? So that was the first question. And the second one was about the kind of going back to the additivity of the quantum measure, the idea that this quantum measure is non-additive. In your answer to the previous answer, you mentioned something like, if you have two regions with one variable each and you add them together because of correlations, you might not end up with two variables. And this idea of correlations was interesting because we usually think of correlations as coming from interactions. And you can write down quantum theories that don't have interactions, that are just free theories of particles evolving completely independently, completely without seeing each other at all. And so it seems like in that case, the phase space should be perfectly should be additive without having to worry about these correlations. And the second thing is, we usually think of correlations as not necessarily decreasing the volume of phase space. We just think of it as kind of mixing things up or changing the basis that you need to kind of diagonalize the system. So I wondered, and there's still a conservation of the total number of degrees of freedom in that. And so I was wondering if you could comment a little bit on how the quantum measure can be non-additive. Yeah.
Okay, let's go back to the first part, which was
the T operator, entropy increasing operator.
So it's not reversible because it's increasing entropy. So for those that know quantum mechanics, it cannot be a unitary operator. It's not something that that conserves entropy, and unitary operation, they're all conserving entropy. It's what is called an open quantum system, like you probably know. So it's we saw before these two equations, right? The Schrödinger equation and then the projection. It's actually a lie. There is another equation, which is the Lindbladian, that allows you to have a process that is not isolated. The Schrödinger equation only applies for a system that is absolutely, completely isolated, which of course never exists. That there is a slight modification, which is the Limblad that allows you to have some interaction. So this entropy production comes from the interaction, and the Limblad operator is just a dagger, and the gamma is just that lambda, the fact. So it's like the simplest thing that you can possibly think. And then the other thing about the quantum measure, so let's think it like this. So let's say that I have, so for those that don't know, the cool thing about quantum mechanics is that a two-state system can be perfectly visualized as a ball. And all the pure state are surfaces on the ball, and the points in the ball are statistical mixtures. So if you take 2 points and you say, I want a mixture that is 50% this and 50% this, you just take the point that it's in the middle, that it's 50%. So you can visualize all the things that you need in quantum mechanics on this ball, understand a lot of things, and then you can mentally say, okay, I'm just going to have more balls. It's all balls. Okay, so if I have this, right, now my quantum measure is going to be something on the surface that counts how many points I have. And it just is, if you take, for example, if you take 2 points, right, you're going to have the point in the middle is going to have an entropy. And the measure that you put on these 2 points, remember, guys, as I said, the entropy is the logarithm of the count of states? Well, since we don't have the count of states in quantum mechanics, but we have an entropy, we say that the count of states is the exponential of the entropy. So we go the other way around. And this exponential of the entropy has wonderful properties that unfortunately, it's one of those things, in the foundation of quantum mechanics, it's funny, because there are a lot of people that keep repeating the same thing for like 100 years. And then there are people like that, oh, somebody in the 90s found this like very nice, completely ignored and remains there. So I'm keeping rediscovering a lot of this thing. And this exponential of the entropy was something that I completely, by chance, I actually went to a couple of conferences and asked, has everybody seen this? Like, you know, the cartoon on the, and no, I've never seen this, I've never seen this. And then on the paper of the classical limit being the higher entropy, a guy called me and he said, oh, actually, you can do this. And said, oh, this is the exponential of the entropy. And he had written a paper in 96 or something like that that showed that the exponential of the entropy is the only measure of volume that has additivity, that has nice property, in both classical mechanics, quantum mechanics, and classical discrete. So he has this proof that basically works. So that's basically what we're doing, is using this exponential of the entropy. And so if you have a region, you basically say, okay, what is the highest entropy that I can achieve with that region? Because in classical mechanics, the uniform distribution over a region is actually the highest entropy that you can get. So it's an entropy maximization, as we do in statistical mechanics. So again, I'm doing the most obvious thing possible. Like, and so you get this, you get a state, because that's the one that has the highest entropy. You do the exponential of that, you get the measure. So if you have a single point, the entropy is 0. The exponential is going to be 2 to the 0, and it's going to be 1, so every point is 1. If I have 2 orthogonal points, it means that there can be 2 results of the same experiment, so they're distinguishable from one another. Then the mixed entropy is 1. You have 2 to the 1, and therefore the count of state is 2, which is what you want. And now if you pick any other point is going to have an entropy that is greater than 0, but less than 1. And so those 2 points are never going to be 2 points. They're going to be like 1.6. And again, why there are 1.6 cases? Because there are not 2 cases at everything else equal. Like if you have outputs of measurement, those cases, you have the same experimental setup, you same everything. And so you can really say, oh, yes, I have this, or I have this. But if you have 2 outcomes that need to have different measurement, right, you need to change the setup. So those 2 things are not at all else being equal. And in fact, if I told you which measurement you got, you will also get information of what measurement was conducted, right? So there is a link between that. And that's why you get this additivity. So in the same way that I said, for degrees of freedom, you're really counting degrees of freedom that are independent, that you can assign the variables independent. For the states, there are 2 states that are distinguishable at all else being equal, or can be prepared at all else being equal.
Thank you.
Okay, next question in the room, and then we'll go online.
Hi, I'm not a scientist, I'm an artist, so I promise my question will be shorter. So I'm a little bit confused about what entropy is. It seems like negative entropy describes things which don't exist.
Yeah.
But my question was, I didn't understand everything you said, I have to admit. But it seems like most of it is just saying that classical mechanics pretends that there are isolated systems, and quantum mechanics recognizes that there are no isolated systems. Would that be a broad correct?
I wouldn't say system, like you're like 50% there.
Isolated
It's
anything at
isolated
all.
preparations, I would say. So that when you're creating that preparation, there is still a notion of interfere from the rest, yes.
So you're saying preparation because the system you're recognizing is not isolated.
Well, because then in physics you do the move and you call the system the part of the object that is isolated.
Yeah, so that doesn't exist, right?
It kind of does. So you can imagine like this, right? That you have, how can I say? Okay, so let's think like this. I have an object here, right? And I have everything else around. I have basically a background, right, that makes it jiggle. And you would say, okay, that thing is not isolated because it's interacting everything and making it jiggle. But that definition of jiggling, right, it's, so let's say that it's jiggle like this. Then I can basically say, okay, it can jiggle like this, it can jiggle like this, and it can jiggle like this. Now, the states are defined essentially of everything that I can say that is not inside the jiggling. So, I'll give you an example, temperature. We have temperature because things are jiggling, right? But when I say I have a gas with temperature, the temperature is defined. Yes, of course there is the jiggling around, but then the temperature is the state. And then I can say that a system is isolated because there is nothing that is changing the temperature.
So the temperature of the system you can say, but you can't say everything about the system is isolated at any time, right?
Correct, yes. So the part that it's isolated is the part that you call state, because that's the one that you can control. And the part that it's not isolated, you pretend that it doesn't exist. And that's where you get into trouble, because then you think that it doesn't exist and said, no, it's there.
And also there might be things affecting it which we haven't discovered yet.
Correct, yes.
All right, moving to a question online. I am aware of a few scientists challenging basic assumptions in the areas of biology, specifically immunology and genetics. They need an organization like physics has. Why do you think assumptions take off as firm truth so easily or are just brushed aside? And how can we better avoid that happening in the future?
What are we trying to avoid? Sorry, didn't get.
Assumptions, sort of I interpret as the dichotomy of assumptions in a scientific field, just taking off as firm truth very quickly or being tossed aside.
Oh, you have to ask that to a historian of physics, of how things work. It's completely mysterious to me. The thing that I've seen in physics very often is instead that assumptions that start as simplifying assumption, you forget that they were simplifying, and then they're taking, oh yeah, it's always like that. That's something that I've seen, and then it's very problematic to go back and say, actually, in the paper, in the original paper, you can see that this was a because the field has basically decided that we're gonna ignore that and so on. So there is a lot of sociology into all of this, and if I were able to figure out the sociology, I would have a project that probably would be 100 times as big, so I don't think the right person to ask that.
Okay, next question in the room.
Great. I really enjoyed this talk. I wanted to ask a question about what role equilibrium played in your sort of description or your mental model. A lot of times when we're talking about entropy, especially in the classical world, we're thinking, and we have this probability distribution we want to talk about, where in this sort of equilibrium, things have settled out sort of state, but we know all kinds of matter exists around us that doesn't have a well-defined probability distribution from which we can calculate an entropy. So in your framework, does that count as just an unprepared thing, or what role does equilibrium play within your framework?
So you hit the nail on a thing that it's always there in some way, and also the word equilibrium is something that probably needs to be, how can I say, revisited to get a new meaning. In the sense, yes, so whenever you say I have a probability distribution, right, and this probability distribution is about repeated measurement, you're effectively saying that there is something that remains the same, both in that finite delta t when you're making the measurement, and both in the repeated, right? So the way that I try to think about these things, which I think is what we mean by equilibrium in thermodynamics, but it's not the equilibrium of thermodynamics where we say explicitly, oh, you just wait the things, right? That does not work because, relativistically, nothing is in equilibrium because, okay, I have the system there, like I start moving in that way. Oh, it's moving, so it's not in equilibrium anymore. No, it's not what we mean. I think that equilibrium, really what we mean is that if you imagine that you have a state that it's therefore some kind of a trajectory like inside a finer description, right? If I am measuring, for example, the temperature, and you imagine that the system is fluctuating during that measurement, and the measurement actually has to be finite time, and it has to explore that finite thing, what needs to happen that all your measurement of temperature, volume, and so on are about the full range. So if you imagine that you took a piece and make a permutation, all the measurement above should not care, right? So what is happening underneath, if I'm going to a higher level description, I'm going to care about the statistical properties of that, but I'm not going to care about the specific. And so to me, the equilibrium is the fact that that you basically have this permutation-independent structure underneath, and all you care is this probability distribution. And if you don't have this assumption, I don't think you can define the probability distribution because it's always changing every time. And if you can't define this probability distribution, you're not defining the ensemble. And if you don't define an ensemble, I can't give you an entropy. So it seems to me that part of that definition of the system, of saying, I have a small delta t, these are the quantities that are stable and so on, has an underneath assumption of my system is in equilibrium. And I can tell you more. In quantum mechanics, we said before, there are these projections that are the measurement. A projector is basically a linear operator that is idempotent. You repeat it twice, and it's the same thing. So if I have a statistical distribution, and I act on it in a projector, the projector over the whole statistical distribution is exactly the same as the statistical distribution of applying the projector of the thing. So the process on the statistical distribution is the same as the statistical distribution applied to the individual process. That's what the linearity is. The idempotent means that every output is, if I put it back as an input, I get the same thing. Now, in dynamical system, if I have an output that I put it back and I get the same thing, that's in equilibrium, right? So you can imagine that the projection of the measurement is actually not a measurement. It's a process that gives you equilibria, exactly the same that you have in thermodynamics. It's all the outputs are equilibrium. In fact, the measurement process can only increase the amplitude, cannot decrease it. So instead of thinking of a measurement as a projector, you're just thinking, oh, it's a thermodynamic process. It's the same thing. And then what is even more interesting is that the structure, the mathematical structure that we give to the state space in quantum mechanics is exactly requiring that for every state, you have a projector that keeps the state the same. Which means, physically, for every state, I have an equilibrium process of which that state is an output of. So you're basically saying all quantum states are equilibria because I'm assuming that there are processes of which they are equilibria of. And then you say, OK, now I can define an entropy, and everything makes sense. So If you explore all these pieces and equilibrium is one of those pieces, then you can start making a picture where all these pieces actually fall apart. And we're trying to build a general theory that basically is the most general that we can make. And the equilibrium assumption is basically there to say, oh, we can define an entropy. Because if I can't define an entropy, I can't count states, I can't define determinism and reversibility because I don't know what I'm mapping to what, and I can't do anything.
Thank you.
All right, we're about out of time, so let's thank our speaker, Gabriele Carcassi, again.